So thank you for showing up to this session. Yeah, just before the conference, there was a symposium in Zinal, which went on for two and a half days. And my presentation is essentially a shortened version of what I presented in Zinal. And I'll begin by defining adaptation, because during our discussions, we found sort of conflicting definitions, and I want to focus quite sharply on one dimension here. So here's one of several definitions that comes from a recent and a very good paper. Any behavior, investment, or other decision taken in direct response to realized or anticipated changes in the climate. All right, so it's forward-looking in the sense you look out perhaps to the end of this century, estimate what's going to happen in terms of temperature, precipitation, and so on. But what the symposium workshop did was to rule out mitigation, right? Because some definitions include that. So I'm not going to, unlike Moise, I'm not going to say anything about increases in greenhouse gas emissions, although that, of course, is a strong motivation for adapting. Yeah. All right, so what I'll do is to summarize the conclusions or what was identified as important ideas during the symposium. And I hope I'm not cannibalizing what was done. Steph is no longer here to shut me up. So 3 or 4 of these lessons come through in the presentation, but there's some additional considerations which the symposium participants saw to be important. The first is that unlike climate change, which is a global externality, the actual effects are heterogeneous, highly. So even 2 locations separated by a few kilometers can experience quite different, particularly precipitation, if you're on the wind side of the mountain versus the leeward side, for example. So that's point 1. Point 2 that Steph emphasized in his work was that not everyone is going to lose from climate change. So it's not uniformly negative. There are some positive aspects to it. And coming from Canada, I know that because the cities can be very cold in winter, and if it warms up, less snow removal is required. You don't have to dress in 4 layers, 3 will suffice, etc. Third important point is that adaptation, in a sense, is an easier problem to deal with because private agents, whether they're individuals, residents, institutions, firms, and so on, have an incentive to protect themselves, right? Because they're increasingly experiencing extreme events such as flooding. So that's point 3. And point 4 is that adaptation can have good or bad effects on mitigation. And an obvious example of a bad effect is air conditioning, because the air conditioners release more heat to the outside than they provide cooling on the inside. So they're contributing to the urban heat island effect, for example. But there can also be good means of adaptation. If you invest in green infrastructure, which can be useful for protecting roads and rail, I think Moise mentioned that in his presentation, then you're absorbing carbon dioxide. So that's reducing, it's preventing some emissions. Fifth problem, which I personally think is particularly important particularly important but difficult to deal with, is when do you adapt? And on the next slide, I'll be identifying 3 types. One is ex ante or immediate. All right, so we now realize that climate change is posing serious threats. We shouldn't wait any longer. Let's do something now. And that means when you invest in new infrastructure, you make it robust for a period of perhaps many decades. The opposite case is where you wait until a disaster occurs, and then you try to clean up and hope that the repair costs aren't tremendous. And then there's an intermediate phase where you're doing something periodically. So you're not acting necessarily immediately, but every 10 or 15 years you're doing something. It seems as if there's no general answer to the question of what's the optimal timing. It depends on the transport mode, where you are, northern hemisphere, southern hemisphere near the equator, whether your infrastructure is new or whether it's already many decades old, etc. And the final point, which I think came out a little bit in your last slide with the parallel routes, it's all very well to protect one link for one transportation mode, but that may be of no use if people can't get there or move on. And that's true of logistics change, for example. So you should look at the whole system. You know the saying, a chain is only as strong as the weakest link. Right? So that means that you shouldn't adopt a narrow, partial view of things. You should take into account other necessary conditions for the service, such as transportation, to continue. For example, in the case of a seaport, you need road and rail access so the containers can come to the port and be moved away from the port. You need electricity, especially if the port is operated by needs electricity, communications, etc. So what I'll do in this presentation is, first of all, identify the impacts of climate change, and I'll try to be brief because Moise has covered that, and then adaptation measures. And then in the symposium, I had a third part, the challenges of choosing adaptation policies. But some of those will come out, I think, in the first two parts that I'll present. So what I'll do is to consider, as indicated in the title of the talk, road, rail, and inland waterway in that order. Now, in the case of roads, there are several hazards. They're identified in the left-hand column: high temperatures, also low temperatures in northern climates, freeze-thaw cycle, where the temperature rises above freezing but then below, and that causes expansion and contraction of the road. It can cause it to break apart, right? So it doesn't last as long as intended. Precipitation, and then sea level rise. And what I've done there is to identify the ways in which the problems are materialized, and the black-blue alternation is just so you can read that middle column a little bit easier. And then, with climate change, are these particular problems going to get worse or better? Well, in the case of high temperatures, for the most part, they're going to get worse because it's global warming, although there can be instances where you have cold spells. Low temperatures, probably not so bad. Freeze-thaw cycles, it all depends on latitude. It depends on whether you're going to a climate where it's almost always cold, below freezing, so you're not going to get the freeze-thaw cycle, or whether it's intermediate or whether it's already pretty warm. Precipitation, it depends very much on where you are, but extreme rainfall is likely to become more frequent, even if the annual amount of precipitation doesn't. So that'll probably get worse. And then sea level rise, that'll get worse, although the amount will vary according to where you are, what coastline and what continent. So here's an example of a cracking in a paved road. Flushing or bleeding, Moise had a diagram for that. Rutting, right? The surface gets soft, and then heavy vehicles will push it down. So it's, and that can increase fuel consumption because the surface is rough. And then that's an example in Manitoba, a province in Canada, of ice roads where for a period of 3 or 4 months during the winter, you have ice on lakes, and then it gets thickened, and then heavy trucks can travel on it. But the season is shortening, and if the truck falls in, then it's a bad problem. Bridge scour. In this diagram, we have the river or the stream going from left to right. And when it reaches a pier of a bridge, you get turbulence, right? So it can speed up, and you get what's called scour. And that means the embankment, whether it's sand or soil or mud or whatever, gets eaten away. And that means that the foundations of the piers, which are supporting the bridge, get undermined. And that's a problem. Now, rail is particularly complicated because there are many things which can be harmed by extreme weather and climate change. 11 components of the infrastructure in the left-hand column. Then you have the mobile plant, the trains which are driving on the track. The staff, the people who run the trains, the people who repair. And if it's very hot or very cold, the work may be dangerous and it has to be suspended. And then, of course, what are the trains used for? To transport freight or passengers. The freight can, if you have air conditioning, it can melt, and then, of course, people can suffer a heat stroke and so on. So many things to protect. So here are the hazards. You can see they're fairly similar to those I had listed for the road. Many impacts. And are there things likely to get better or worse? Well, for the most part, worse, although with the exception of the low temperatures. And here's an example of buckling. The the rail expands in the heat, and it can no longer remain straight, so it gets curvy. And if it doesn't curve in a parallel fashion, the gauge of the rail can get bigger or smaller, and then the train can derail. What about inland waterways, which is an important form of transportation in Europe? The Rhine stands out as the big case. Well, high temperatures are a problem, and less water, as described in the left-hand column. That's the main problem, which leads to drought. The drought means that the water level shrinks, and the barges with a high draft, they can no longer operate. So either the load has to be reduced, or they get replaced by smaller barges. And that means an increase in cost. It may be possible in some cases to shift mode to the road or the rail, but it's not efficient because the barges can carry hundreds, even thousands of tons, and it takes a lot of trucks or trains to do that. And then they're more less fuel efficient, so bad for the environment. All right, so things could get better, but more likely to get worse. And here's an indication of how you determine the maximum draft of a vessel. In the interest of time, I'll skip it. That's a schematic for the Rhine. So let's go into adaptation. Now, as I mentioned, there are really 3 time intervals during which adaptation can be classified. Ex ante, which I said was just you build things new, right, so that they are robust, resilient, so they can withstand more adverse weather and climates in the decades to come. Ex post means when there's buckling is a threat, you reduce the frequency of trains, you reduce the load, you reduce the speed, so the lateral forces on the rails is reduced. And then in the middle, there was some pushback from other participants in the symposium as whether this is a useful third category, but I think so, because adaptation is not always right now or wait until a disaster occurs. So what you might do is to wait until some threshold is reached, right? So sea level rise has gone up by 50 centimeters. It's too dangerous to let it go further, or the frequency of heat spells, extreme weather and so on, that's become frequent enough that you really should do something. And you may do it now, and then 10 years, 15 years later, the threat has gone up again, so you take further action. In some cases, it's not obvious whether you should categorize something in this middle, periodic or ex ante or ex post, but I think it should be considered. Well, yeah, if you can't deliver freight to the destination for some time, then if you have bigger inventory, then it'll take longer before it runs out. So it provides some security to the supply chain. So that's for freight, not for passengers. All right, so what about the ex ante, periodic, and ex post measures? We can see there's a lot of them. I'm not going to go over them, but it indicates that there are many ways in which you can protect, so it becomes a difficult decision perhaps as to which measures you're going to deploy and when. And here's an example of what's called riprap protection. I had to look it up in Wikipedia when I was preparing these slides a few weeks ago. It's simply boulders, which may weigh several hundred kilograms each. They're not connected to each other, they're just piled up, and it slows the water so it's no longer causing the scour. And if you look at rivers, quite often you see this riprap. So there are several case studies showing the ways in which adaptation can occur and how useful it is. And here's one of roads in well, it's actually the whole infrastructure in Alaska, and projecting out to the end of the century, what the dangers, what the damage likely to be, and then how we do go about protecting the infrastructure so there's less of a loss. And in this case, it was found out that roads are the form of infrastructure which is mainly vulnerable. It's not rail, it's not airports, and it's mainly precipitation. So what they determined is that you got to protect the roads, and if you do it by improving the drainage, you can almost eliminate the cost. So it's a sort of good story that you only have to worry about one mode of transport, and you only have to protect in one way. All right, so that's sort of good news about about adaptation. Another example also from the US, but countrywide, looking at bridges, again to the end of this century. And then the question asked is, should you be protecting ex ante or ex post? And the answer switched at mid-century. So up until 2050, ex post was determined to be cheaper. So you wait until there's a problem and then you fix it. But after that, ex ante was cheaper. So you don't wait further. You either replace the bridge or you bolster it. And that wasn't intuitive to me, and I couldn't see an explanation in the article. But again, they're clearly addressing an important problem. And then the third is a paper which I don't think has been published yet, but done very well. And it was looking at firms in Pakistan subject to flooding. And how might they respond to instances of flooding? Well, there's several ways. The first is to relocate their own facilities to safer ground. That's pretty clear. The second, concerned about the reliability of their suppliers. Right? So if the suppliers get inundated, then the inputs this firm required will be disrupted. So what they do is they switch away from those vulnerable suppliers. And the third is not only the switching, but they be adding more suppliers, so sort of spreading the risks. And then the fourth, which is most relevant to this presentation, the roads connecting the firm and its suppliers may be vulnerable. So even if both sites are safe, in between, if the roads get inundated and they're impassable for a period of days, that's bad news. So what they would do, the firms, is to shift purchase away from the suppliers that are connected by the vulnerable roads. And I think there were 6 billion observations in this study, so results statistically significant. And of interest is that the floods might be over within a few weeks, but the adjustments are permanent, so they don't go back to the previous supply. So there's hysteresis, or if you like, learning that we have to do things differently from now on. Now, as far as rail is concerned, I classify ex ante, periodic, and ex post. I won't go over the details, but you can see it's mostly ex ante. Right? Just a few examples of ex post there in response to extreme heat. Winter weather, high precipitation, droughts. Now there's more periodic ways of adapting. And then in response to extreme winds and wildfire, there's a bit of a mix. So you can see that there are many ways in which adaptation can be implemented. It depends on the threat, and the timing, again, is a big but clearly important, big and clearly important question. Now, what about the nature-based solutions, which would involve planting trees or some kind of vegetation along the rail bed or along the roadway to provide some protection? Well, that can be done in two ways. One is let nature take its course, mangrove forest, for example, and then green infrastructure in urban environments, right? So roads and possibly rail lines, and it has co-benefits. Right, so as far as protection, you're protecting against stormwater runoff, protecting the shorelines, maintaining the diversity of the biological species, but you're also reducing emissions, as I said a while back, as well as water pollution, air quality, and noise, right, because the trees will sort of block the noise. And then there's some aesthetic benefits as well. So this is an instance where, if you like, there's a coordination or supplementary benefits which should be taken into account if you're doing a cost-benefit analysis as to whether this particular form of adaptation is going to be useful. Inland waterways, you can see there's a smaller set of measures of adaptation, but again, ex ante, periodic, and ex post. And then I'll conclude with this nice case study. So a fairly recent study looking at the effects of a very severe, 5 minutes, that's good, a serious drought which occurred on the Rhine for much of 2018. And the section of Rhine, I guess Rotterdam is the mouth, and the question is, can you get goods to and from Duisburg in Germany? And what the study did was to do a simulation study looking at the amount of flow into the Rhine at this town of Laubeth. So the line shown in the top is the actual discharge rate, so how quickly is the water coming into the Rhine, measured in cubic meters per second. the beginning of the year when you get runoff from or glaciers, if there's some there and so on, gives you it's very high, over 7,000 cubic meters per second. And it oscillated, but by the middle of the year, it had dropped to about 1,000, right? So just a fraction of what it was at the beginning of the year. What the authors did was then to simulate the water depth. They didn't actually have measurements, but they had reliable software to do it. And you can see it was almost a mirror image of the discharge rate, of course, with different units of measurement. Now, the biggest barges require 4 meters of draft. And you can see by the middle of the year, it was no longer there. So you had to switch to smaller barges, which are less efficient, right? They sacrifice economies of scale. The number of trips jumped up considerably at the middle of the year, but that doesn't mean that more freight was being transported. Rather, it was going on smaller barges. So these are trips by smaller barges that could carry less. And you can see that on the top right that the volume was dropping slowly for much of the year, and then it dropped to almost zero. I guess that's October and November. Cost went way up from about €1 per ton on that route up to about 7. So clearly a severe economic cost during the second half of 2018. And then here we see the type of barges which are being used. The best ones in terms of scale economies are the 6 barge pushed up, shown by the solid line, and they were operating until mid-year, and then they stopped, right? Because even if they're empty, they couldn't have navigated the Rhine. There was a switch to the 4 and 2 barge push tows, an intermediate size, and that's shown by the dash line, but you see that dropped to 0 towards the end of the year because even those barges couldn't make it. And then you had these other smaller types, Rhine vessels, coupled barges, which took over. But the volume did drop considerably. And then the network effect that Mo was hinting at was relevant here. You have a lot of, many more smaller barges going to Rotterdam, and that was causing congestion, right? Because the congestion is not just a function of the vessel size, but how quickly it can be loaded or unloaded, and having berths. So the vessels can stay stationary until they can be serviced, and also a reduction in inventory. So some shortages occurred. So this is a repeat of the general lessons slide that I had at the beginning of the presentation, and I put in blue those which are, I think, addressed to some extent in this presentation. So that's it. Thank you. Thank you.